Hi everyone. Today we are here to discuss about the solar generation forecasting using machine learning and AI techniques. Um, uh, Myself, Banu Prakash, and then my teammate Fananda Reddy, we both together did this project. So coming to the introduction, um, as the growing global energy demands, the agents need to reduce the greenhouse gases emissions. So the renewable energy source like solar power comes into the action because it has more potential and then so rapid technology advance. So both of like government sector and private sector are growing this solar power, utilizing this solar power to reduce the fossil fuels and also to combat the climate changes. So, but there are many challenges in this solar energy, like insulation and also like the power grid problems, and also due to the like weather. It heavily depends upon the weather conditions, and also such as like sunlight intensity, or there may be cloud coverage, and also there may be temperature dropping. Throughout the like day ins or day outs, due to these issues, there are many challenges this solar power is facing. So there should be more need of accuracy forecasting, so that they'll be like discussing. Today we will be discussing about the energy distribution, about their storage and the management, and all these things in the accurate forecasting. So coming to the background, solar power is mainly used the technique called PV cells, which are if you see in this picture, which are arranged in the PV arrays, and then sunlight is taken from light is taken from the sunlight, and then which is transforming, like converting into the batteries, and then it gonna convert to the power grid. From that, it gonna transfer to the transform, and then the current is supplied to the towers lines. So there are environmental effects due to this, which are weather conditions, as I told before, and also temperature effects, and then the seasonal variations, and also the implementation. I mean, the impact on the power grid management is the grid insulation challenges, and also demand and supply balancing, and also energy storage and forecasting. These are all the impacts on the power grid management. And the problem statement is like unpredictable of the solar power, like it heavily depends upon direct sunlight exposure, which is unpredictable due to the various factors, and also the range, uh, due to very short period of output generation, and then the forecast difficulties or complexity of accurate prediction modules, and it mainly depends upon the technology, but it is which is more expensive, and also the technology is like demanding. And the primary objective is to enhance the accuracy of the solar power forecasting by using and comparison various machine learning techniques and modules. And this enhancement will support more reliable and efficient solar power integration into the power grid. And the secondary objective is to mainly focus on real-time forecasting capability and availability, and also the scalability. In the literature review, current forecasting methods is having limitations on the scalability issues, and also data dependencies, and also due to the various underperformance calculations. And coming to the machine learning approach, it mainly depends upon the nonlinear relationship and also time series. Traditionally used for the solar forecasting, time series method like AR, IM, and then it predicts the future values. This method assumes that it also depends on non-linear patterns. It does not depend on a linear pattern. So these are the issues in the file method. And coming to the methodology, we took data collection like uh, from the source, which is which is having all the solar power consumption data of the one city called London in Europe. And the duration we took, you gonna take for every 15 minutes the data is been captured for all seasons and various weather conditions, and also data pre-processing. We did the cleaning and transformation process. In the evaluation matrix, we use the matrix models like to evaluate based on mean absolute error and also root mean square error. These two matters we have used to understand and predict the accuracy or error magnitude. And coming to system design and architecture, first we took the data collection, and then we did the pre-processing and model selection, and then we trained, evaluated, and evaluated, and then we did the same process until we got the accuracy, and then we generated the final module. So coming to the implementation, software and libraries we used, those are the Python and Pandas for data manipulation and analysis, and NumPy for numerical data handling, and MATLAB for data visualization, and then training evaluation. The performance metrics, like as I told before, MAE and RMSE, are used to evaluate and compare model performances. And optimization techniques or discuss like any techniques like grid search or random search used to turn the hyperparameters. And data pre-processing used to handling the missing data and future extractions. So features and like mention any new features that are like engineered from the data sets were being considered as important. So and also normalization and standardization, like described how the features were scaled or normalized. And coming to the details part, and then implementation, how the graphs are explained. This gonna explain by my friend, like other teammate. Mm, and thank you.
Hello everyone. So our project is based upon solar power forecasting generation using machine learning and artificial intelligence. So my part is to gonna explain the code that what we did. So in this code, so the we uses the basic libraries called NumPy, Panda, MATLAB, Scikit-learn, Python, and some other things where you can see all these things over here. So basically, at first I'm gonna run this one, so which is will install all the required libraries over here. As you can see, a requirement already satisfied. So after that, when we gonna upload the data that what we used to put it, so this is my data, so I'm gonna put this. It's going to show a warning sign, so just neglect this one and click OK. After that, run one by one. So here you can see, so this will run one by one here, so through which where we can see the graph has been plotted for the data which we have taken, and you can see the RMSE and R square values over here. So which means the predicted values and the actual values, where the RMSE is 3904.27, where this is for the linear regression. So when we used to run all at a time, so it will run all the codes which are there at a time. So here it will asking me to upload the data once more, so here once more I'm gonna upload it. Here after the uploading it will modify and it will automatically generate the data graph for the input what we have given. So it's gonna take some time. So this code is for the linear regression, which will plot the graph for the actual predicted power and predicted DC power over here. So here you can see, so the linear regression is 394.27 kilowatts, whereas you can see the decision tree RMS is 139.495, and the R square is nothing but a predicted value which is 0.87, like 87% of the predicted value is correct. whereas for the random forest RMSE 944.06 kilowatts, and the predicted value is 94% accuracy. So this R squares shows the accuracy, that how much accuracy your predicted value will be. And this is the graph for which the data we have taken. So these are all the points, like there are thousands of points. I just took the data for an year, and in which for every each 15 minutes I'm gonna have the data of the solar power forecasting. So this is gonna be the bar graph for hour, how much it's gonna be, and per monthly how much it's gonna be produced. Where similarly this is gonna be the tree chart, that how does the sequence work, and how I plotted the graph. Depending upon that, we have built the tree diagram over here. That's for the linear regression, and this is for the random forest model. In this too we will have the bar graph and the pie chart, for which the energy distribution per month has been plotted. So you can see for 1 to 12 months, so every month there is gonna be some percentage of distribution of power of solar, which have been plotted, like 6.8% for the first month, 8.7 for the second, 8.8 for the third. Now when we come to the random forecasting method, so you can see the bar graph, and this is going to be the predicted and actual value for this. So you're going to see here 94.40.6 kilowatts for random forest, and the predicted value is 94% accuracy, which means 94% of the predicted value will be the correct. So here you're gonna see the data that we took and the predicted value. So the predicted value is going to be 94% correct for this time for the random one. And similarly for the tree diagram, that it will show you how to plot the diagram. And this is going to be the pie chart for it. So similarly I plotted the energy distribution of solar for every month of an year. So similarly, I used to compare both the method, the linear regression method and the random forecast method. So you can see both the methods in a similar graph. So the green dots is the random forecast, and the blue dots is the linear regression, where the dotted black line is the predicted value. So for this, I didn't get that. So, and this is gonna be the tree chart for it. And I compared both the models, the linear regression and the random forecast method, through which the energy distribution varies. And this is the bar graph for it. So the linear regression is 4.5% high, whereas the random forecast is above 4 and below 4, above 3 and below 4. So actually these methods are used. We can also use the polynomial regression method, but due to the data we don't have the calculated part, like we used to calculate the data for each hour, so we don't have that. So due to that we cannot able to have the polynomial regression. So I just use the linear regression for the accuracy part, and the random forecasting method for the machine learning and AI tools for it. So that's all about my project. So thank you.